So that is the general idea, and I guess we can try to work through the full um, the full symbolic version of it. So if we have our general case, x squared plus bx plus c is equal to 0, then we need to get the x squared by itself. That's one thing that I didn't show in the example. It is a little bit more difficult, but it's pretty straightforward if you think about it. You have to just divide an a out of all of the coefficients and constants throughout the actual equation, and then you can do the rest of the problem that way. The problem that arises a lot is that we will get a bunch of fractions, and when you divide things out, sometimes they don't divide as nicely, so it can become a little bit more confusing in the long run. But we should see that this should equal out to exactly the same thing as the quadratic equation. So if we have bx over a plus c over a, and we are equal to 0, then we're going to move this ca to the other side, x squared plus bx over a, and then we're going to divide this by 2 and square it. So we're going to say that this is b we're going to say bx over 2a squared is equal to our negative c over a, and then we just have to subtract, or we just have to factorize this. So if we are doing the factor of this, then we'd say that x plus b, sorry, not bx, just b over 2a squared is equal to our negative ca over a. I'm sorry, I actually forgot a step here. So because we added this here, we actually do have to add this to the other side as well. So this will be plus our bx over 2a squared. So this is to keep things even. So here we had this equation, and we've just added this term to this equation on both sides, so it's still equal. And then we've moved the c over a to the other side. And then I might actually put this actual proof as a secondary video. I'll see how long it ends up being. And so we are at this point, and we have bx. I'm sorry, I'm not sure why I put an x here. So if you remember our form, then it's just the coefficient that matters. So it would have caused some problems if there was an x on both sides. All right. So we have our b over 2a squared, and we want to take the square root of both sides. And so we actually, let's just square this out to begin with. So if we, sorry, I was hitting the redo button. So we're going to have a b squared over 4a squared. That's important. So we have, we're going to do the square root of both sides. So we have the square root of this whole combination of fractions, and then we have x is going to be equal to negative b over 2a plus or minus the square root of, we have our negative c over a plus b squared over 4a squared. So we have to try and move this around a little bit in order to get it to the form that we want it to be in. So it is actually starting to look a lot like our negative b plus or minus the square root of b squared minus 4ac over 2a. That's the goal we're going for. So now we have the first term. That's pretty straightforward. So we can see that right there is already here. We just need to work on this this radical so that the determinant actually equals out to that. So if we take we're trying to take a 1 over 2a out of this so that we can work with what we have. So if we are dividing, if we're factoring out 1 over 2a, so that's what we're doing here. We're going to divide both sides, we're going to divide this fraction, this radical by 1 over 2a, then we're actually going to multiply everything inside of it by 2a squared, so that we can factor it out. So this next step we're going to say is equal to negative b over 2a plus or minus 1 over 2a, because we want it to have the same fraction here. And then, so if we have 2a squared, that's equal to 4a squared. And so if we multiply this first term by 4a squared, one of the a's cancel. We're going to have a negative 4ca, and then plus 4a squared is actually the denominator here. So we just have a b squared, and we should have what we have up here. So if we just rearrange this a little bit, then we have our x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So that is why these two methods of factorization are equivalent, and they are both universally applicable. So they work in any case where you're dealing with a quadratic polynomial, and they will give you the answer no matter what, although sometimes those answers will be complex. So like in our example earlier, you can get a negative under the radical and you'll get a complex number. But if you are just dealing with a nicely made quadratic polynomial in an algebra question, odds are it should work out to having something in the real numbers. So that is our proof to show that completing the square is equal to the quadratic formula. And at this point, I'm going to be moving on to my random drawing section, but I hope this was helpful in understanding the completing the square. And